An object is placed 30 centimeters from a convex lens with a focal length of 10 centimeters. Find the position of the image. What is the magnification of the, that should say image, not object. If the object is 3 centimeters high, what is the size of the image? So this right here should say image. I messed up when I typed that, so that's image. All right, so of course this is a convex lens, which is a converging lens. That means F is positive. So it's going to be 10 centimeters. The object distance P is 30 centimeters. P is always positive for us. We're trying to find Q. Now, if Q is positive, it's a real image. If Q is, and that means upside down. If Q is negative, that is a virtual image. That means upright or right side up. So we're going to use the equation 1 over F equals 1 over P plus 1 over Q. And just plug in. So 1 over 10 equals 1 over 30 plus 1 over Q. So 1 over 10 minus 1 over 30 equals 1 over Q, and Q is going to equal how many centimeters? Well, I just put that in my calculator. 1 divided by 10, no parentheses or anything, minus 1 divided by 30. I get 0.0666, but I hit X to the negative 1 to flip it over, and I get 15. So Q equals positive 15, positive 15 centimeters. That means it is a real image, and that means that it is upside down, down. And then the second part of the question is, what's the magnification? So the second part is magnification equals negative Q over P. And so that's going to be negative 15 centimeters divided by 30 centimeters, and that's going to be negative 2. That means that the object is, or the image is twice as big as the object. That's what that means. And so the third part of this is, what is the size of the image if the object is 3 centimeters high? Well, that's going to be HI over HO equals magnification, which in this case is 2. So that means that the image is twice the size of the object, so that would be 6 centimeters would be HI. If the object is 3 and the image is twice, then the image would be 6 centimeters. And let's just talk about a few more things here. Of course, we have different kinds of lenses. We have a converging lens, which is a convex lens. And what that means, it means that light coming in parallel like this converges to one point that we call the focal point. And that focal point has a focal length that is from the center of the lens out to the focal point. Call that F. So this will always have a positive focal length, excuse me. It can have a positive Q or a negative Q. It can have both. Of course, this is a positive Q is a real image, negative Q is a virtual. The virtual image is always larger. Virtual. It's a magnifying glass. Virtual, larger. And then these are real images, which can be all sizes depending on how far away you are from the screen and object. The other type of lens we have is the concave or diverging lens. It looks like this. In extreme, it looks like an apple core, sort of, it's been eaten. And so this is convex converging. this is concave diverging. And so light rays that come parallel in with the optical axis here are going to go out like this. And theoretically, if this is done right, we should be able to make dotted lines back this way, and they all make what we call a negative focal point. So from here to here is a negative focal point. So these always have a negative focal point, and they always have a negative Q. It's always a smaller virtual image. There are no images that are real in this case. And then the last thing that we did in this chapter, or actually the first thing, not the last, was refraction, which lenses refract. That's the way they work. And so if I have air and water, and there's my normal line, the imaginary line that's perpendicular to that, to the surface. And I have a light ray that comes from air, which is 1. And let's call that 40 degrees. Then what's going to be the angle here? Well, first of all, since this is n equals 1 and this is n equals 1.33, it's going to bend toward the normal. It's going to slow down, and it's going to change direction in a manner that this angle here, which we'll call theta 2 or theta r, is going to be less than 40. And so how do I find that? Well, I just use Snell's law, which is N1 sine theta 1 equals N2 times sine of theta 2. So N1 would be 1 times sine of 40 degrees equals 1.33 sine of theta 2. You have to be in degree mode to do this, so it's going to be sine of 40 divided by 1.33, and then that's 0.48, then I'm going to do inverse sine of 0.48329. That gives me 28.9. So that theta 2 indeed is smaller than 40 degrees, which is what we said. Okay, that's just a general overview of Chapter 14, optics, or actually refraction and lenses.